Welcome back. Suppose that I have an LTI system. This second term is the input term. For the design of controllers, only control inputs are considered. But for getting the system's total response, it can be a control input, a disturbance input, or both. Getting the system's response is another way of saying solving the differential equations that describe my system. So let's solve the state space differential equations. If I assume that my states have initial conditions x0, then using Laplace, I have this equals this. So I've taken my LTI state space equation into the Laplace form. I can rearrange it in this way, where the term with a times xs goes to the left and then the initial conditions term goes to the right. I can then factor out my x, which will be this, and then I want to solve for xs, and you can do it in this way. And so here, of course, you will have an identity matrix, and so in the end, your xs will be this one. In literature, this inverse matrix is also denoted with big phi as a function of s. And now, to take x in the Laplace domain to the time domain, you have to take inverse Laplace of it. And so, you will have Laplace inverse of x, which will give you your x in the time domain, which will be the Laplace inverse of this term plus the Laplace inverse of this term. Since x0 is a constant vector, you can take it out of the Laplace inverse operator. And so, you will have Laplace inverse of this matrix here times x0. Now notice that this one is a matrix, and when you take Laplace inverse of a matrix, you are essentially taking Laplace inverse of each of its matrix elements. And it's easy to see that. Let's just take this random system. If I take Laplace inverse of x1, then I will be taking the Laplace inverse of this entire thing, which also means that I would be taking the Laplace inverse of each term, but since x10 and x20 are constants, I would be simply taking the Laplace inverse of as and bs. And then I will do the same thing with the second equation. And now I can package it into a vector, and this is what I will have in the matrix form. So this vector here, it will be this one, and then this matrix here, this is like this one here. And as you can see, when you take the Laplace inverse of a matrix, then you're essentially taking the Laplace inverse of each element of that matrix. And now, in the first term of your solution, the Laplace inverse of this matrix has this form in the time domain, which means that the entire first term in the time domain will be e to the power of matrix A times t times your initial condition vector. This matrix here, it's called the state transition matrix. This matrix maps the initial states of the system to the states at some other time. Remember that this vector is simply your state vector at time equals 0 seconds. Note that in the time domain, the elements of this matrix are also as a function of time. So this is the first term. But now, let's look at the second term. So in the second term, you can see that you have a multiplication in the Laplace domain. But in the previous course, in the differential equations section, you learned that multiplication in the Laplace domain is a convolution integral in the time domain. Therefore, this term looks like this in the time domain. Therefore, my total solution in the time domain equals this term plus this term. This term here, it's your response from the initial conditions, and this term here, this is the response from the inputs that can be control and or disturbance inputs. So for LTI systems, the system response is given by this formula. Note that calculating it in the time domain is not easy, especially the second term. Therefore, you should start with Laplace and then take Laplace inverse to get the system response in the time domain. Now, the state transition matrix looks very much like e to the power of a times t, where a is some constant. But remember, this is an actual matrix, and this is simply a function. And you will see that in this matrix, each element will be a function that will depend on time. Also, be careful with something. You know that if you multiply this function by this function, then you will have this result. However, in general, the same is not true for the state transition matrix. In general, if you have this matrix times this matrix, it will not equal this matrix. And so, this matrix would be this matrix times this matrix, and then this matrix would be this one, and there is no reason whatsoever why these two results should in general be equal to each other. In some exceptional cases they might be the same, but in general that's not the case.